Hello, my name is Chris Blask, and I'm your host today for this episode of the Inevitability Curve, where take a topic, we look back in history to see how we got to where we are right now. We take a look at that, and we look forward. Joining me today is a good friend and colleague, Tim Roxey. Tim, if you don't know who Tim is, look up the name. It's a fascinating ride. Keep your hat on tight for it. Tim and I met in the cybersecurity realm when we were, I think, working at NERC, the North American Electric Reliability Council, which has paved the way for cybersecurity regulations and power grid uh, around the world. But as we were discussing in the green room before this, the topic of AI and infrastructure is something that we can have fun with. So I'll let you choose exactly where we start, but where have we been in this space, and how do you think we got here?
Yeah, so get into the space of artificial intelligence, you have to think about what the alternative to artificial intelligence is. Of course, it's real intelligence. That's you and me and others. On good days, we're okay, smart monkeys, and on bad days, we're not so good. We do bad things, but here we are, humans, and then in one of my career paths as a nuclear engineer, that's my engineering degrees are both in nuclear engineering. We study a lot of pretty arcane things, mathematics, symbolic logic, blah, 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 a bunch of stuff, boring stuff. But the fundamental reality is that you have these nuclear power plants all over everywhere, a bunch of them. Used to be 104 of them in the United States on 64 sites. So how you control nuclear power plants is very important. And the industrial control systems for these nuclear power plants fall into two or three broad categories. The one I focus on the most was nuclear safety or safety-related category. Those are the ones that are really, really important. But that's just industrial control systems. It's in all 16 critical infrastructures. It's everywhere. But where have we been in that is really stone knives and bearskin rugs, but done very well. Really nice stone knives and very cool bearskin rugs. We have a safety analysis report for a nuclear power plant, and that safety analysis report has a collection of design bases. The pumps will be so big, the pressure vessel will be so thick, the containment building will be so large, it will be able to do this. And based on the general design criteria, these design bases turned into engineering specifications into build specifications, and nuclear power plant comes. Operating the nuclear power plant, though, you have to stay within certain parameters, lots of parameters. And real intelligence breaks those systems of a nuclear power plant down into system structures and components clumped into functions. So there are primarily fission barriers, the fuel pellet itself, the cylindrical tube that it sits in, the fuel assembly, the reactor pressure vessel, and the containment building. All of the nuclear power plant regulation is around how to prevent the nuclear reactor materials, the contaminated materials or the radiologic materials, from escaping into the general public. Industrial control systems control almost all of those processes. Over time, we've gotten extremely good at the industrial control systems around, I think 1980-ish. So where have we been? 1980-ish. What we would consider today machine learning started to rear its head, which was kind of interesting because we had algorithms that would control flow rates and all kinds of stuff. So software, stuff I grew up on, writing software for different control systems. That software would control the operations of or the design of parts of the nuclear power plant. As time progressed, we had industrial control systems, the boxes, the widgets became powerful enough that you could start putting a lot of extra software into those. So we wrote software for those boxes. All of a sudden they became very intelligent field devices. Then along comes artificial intelligence, and this is in the 80s. It wasn't called that. It was some of the terms we used were inference engines and rules-based. So rules-based, what is the basis of operating a nuclear power plant? And then an inference engine which can be considered to be something like a fuzzy logic module, which is going to process an operation into a smaller set of tokens, which can be understood by the endpoint machines, and a physical manipulation of a device would occur as a result of all of this. These became quite good. Then, in a completely unrelated field, there were some experiments done, I think, in the 60s and early 70s, where a series of circuits were created. I think 40 was the magic number in one of the books I was reading, where rather than program a computer system to give you a result based on an input, like recognize the letter E, rather than try to do that, you instead create a neural network that you expose a letter E to, and then you adjust some bias controls inside of this neural network mesh until you get a +1 or -1. And you teach this group of 40 circuits how to recognize the letter E in different orientations. Kind of cool. You have an emerged behavior off of a collection of hardware that we'd spent literally decades trying to write software around, very smart, intelligent software that would be able to do this recognition pattern. Whereas if you do it this other approach, there's no software programming per se. What we've now done is program those little circuits, 60 to 100 lines of code, and collected them in certain ways in which you can now expose a letter E to a set of optical scanners on one end, and you will get a digital output of a letter E, no matter which way you turn it. That's voice recognition, that's speech recognition, that's text recognition, those CAPTCHAs that we've been trying to correct for years and years and years. Are you a human? Those are actually this huge archive of letters and or words that have confirmed human intelligence, that has confirmed that that is indeed bicycle, or that there are so many bicycles in the walkway, or whatever. Anyways, those huge databases now go into training these artificial intelligence engines, which are now being applied to industrial control systems. And the interesting part to me is we are way out above our skis, so to speak, because back to the basics again. You have a design basis of a nuclear power plant. You have a design base accident. What's the worst that can go on? And then you have a way to protect the public from that design base accident. That's all written inside of the final safety analysis report. The reactor is built and operated so that that protection mechanism is always front and center. You're always going to protect the health and safety of the public. Fast forward now to a very deterministic approach. We know what the design basis was. We postulate what a design base accident is. We assess the hell out of a design base accident, and we create a scenario in which we can protect the public. Very deterministic. Boom, 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 boom. The equations, although complex, are solvable for most cases. So it's a doable, deterministic thing. However, when you have machine learning, you can mimic that process very, very well. And some of the coefficients of the algorithms of that machine learning program can be adjusted every time you execute that cycle. So every time an industrial control system loop goes through, you can make a tiny adjustment to those coefficients in the algorithm. By doing so, machine learning control systems can actually learn to adapt to the environment. That's different than a generative AI. Generative AI gets weird. That's where you're going, is taking some of these industrial control systems that have very deterministic things, and you're going to bridge that gap across an emergent behavior, and you're going to look into the generative form, which is going to sound nice, but may have some issues like biases, like hallucination, the things we've been seeing in the AI world. The question that was put to me several years back now is, where would you put a bright line criteria in the industrial control system for safety-related industrial control systems, like you find in nuclear power plants, where would you put a bright line that says that you're allowed, you should be incentivized to put in really elegant machine learning solutions because they're very fast and very strong, very deterministic at some level. And where would you be able to use a generative component like we've seen in chatbots and stuff? Where would a generative component be used? Remembering that the generative component, that emerged behavior brings with it all of these weird behavior problems like hallucinations, just completely out of scope stuff. So how do you apply the indeterminate characteristics of artificial intelligence, generative, to a far more deterministic set of controls for industrial control space that is operated by real intelligence?
Right. And this is, as I thought about this one before we started recording here, I think there's an argument to make that we've been building artificial intelligence into infrastructure for thousands of years, right? You take the earliest, water systems, you find out that if this water goes beyond a certain level, that's a bad thing. You put a notch in the rim, we have an overflow valve. So we're replacing what a human would have done. If I'm sitting there watching the water level up, I'm, draining it, I'm pulling out the log, I'll just build it in.
Mhm.
And you can follow that arc up to, the Industrial Revolution. I'm always fascinated with Joe Screwdriver's Retrotech Time Machine on Roku, which plays all these, training films and documentaries of industrial processes since the early 1900s, and things like World War II battleship artillery calculators, which are these analog machines. You rotate this knob and this gear turns, and the math is worked out,
Mhm.
which is taking the intelligence a person would have used and just automating it, making it artificial. And I think you led up very well to where we are right now with what we're calling "quote unquote" artificial intelligence. Right, and there's this
One
deterministic,
of it.
right, and I find it fascinating as well that, as you and I did some work in South America a number of years ago, and just before I went down there with you, I've been working with Colombia, which is public record, and made a 25-year national infrastructure plan. And at the 7 and 15-year marks, I felt it worthwhile calling out certain things. And this is really effectively one of them. Artificial intelligence, information integrity. Win Schwartow and I last week on the show were talking about where we are with with information warfare, what he's terming as meta war, and it's the same sort of emergent property issues. Where we have not, through all the things we can look at through human history, we haven't really actually encountered this one yet. So where we are right now, in this, what do you think? What do you think the main misunderstandings, misconceptions, if you like, or the opposite of that? What are we getting right now and thinking about this? That bright line, or are we clear on how far we can go with generative AI as a managing critical systems as opposed to deterministic?
Well, oddly enough, right now we're still at the very, very earliest days. I mean, artificial intelligence is an umbrella term that means a lot of things. One of the bigger components of it is machine learning. Machine learning is actually a subordinate component of generative AI as well. So OpenAI and others, the generative forms. They have these subcomponents within them who do other parts. And there are, as you said, decades of experience with machine learning kinds of things, like a notch in a pipe that gives you a certain level, and beyond that, your toilet has one in the tank, right? A ball valve. But the things that can be done with where we are today is, imagine, if you will, you're the system engineer for a turbine control system, and the analog computer that you use is an electrohydraulic computer. So some type of electrical components, and hydraulic, some kind of fluid. So to operate an electrohydraulic control system, it's a lot of work. You got electronics, you got electric, and you got components like the viscosity of an oil, specific gravity of the oil, the purity of the oil, blah, blah, whatever the working fluid is. And then someone comes up to you and says, hey, I can do this whiz-bang thing here with these flashing lights, right? And you go, wow, that's pretty cool. So in the world of engineering, we would look at the parameters, the basic engineering design criteria for the electrohydraulic turbine control system. And we'd say it is this. These are the requirements that thing has to fit. And then you have material requirements like the metals and blah, blah, all this stuff. So when you're done, you have an operating electrohydraulic turbine control system. But with the bright lights and flashy lights, the thing that wasn't said before was deterministic. In that EHC, it's very deterministic. If these are your input criteria, this is your output position. Your pound mass per hour into the turbine is this, right? If this is it, okay. So you can make an electronic version of that, which is very deterministic. So for a certain pound mass per hour coming in with a certain saturation of the steam, you have a certain energy density, you have turbine blades, which are still the same, you have rotating parts, which are still the same, you have a specific output that you can get to. Very deterministic. If this is your input, that's your output. When you get to another component of artificial intelligence, not the machine learning component, which that was working on, you get into the generative forms, all of a sudden, the outputs can be generatively driven back into the inputs, so you can dynamically take into account certain types of behavior that may emerge. So don't get ahead of your skis on this one, but just taking the electrohydraulic control system into the electrical age, making a digital control circuit, gives you opportunities now to take all of those transducers. Imagine the 15, 20 different touch points on that turbine control system, the actual turbine and the generator. The 15 or 20 engineering touch points where you go in and sample the temperature, you sample the pressure, you sample the turbine speed, you sample the pound mass per hour coming into the turbine. Imagine all those touch points now building up databases of all of that information, driving it down into the data. And then horizontal to that, you have this generative component, which is looking across all of that data. A generative component, mind you. So you can have a conversation with it, right? Not the machine learning component, which is going to be sitting there looking at this input, same thing, looking at the input going, I hit a trip set point. I'm going to flip the reactor off. I'm going to stop my input energy. I'm going to trip the plant and go into a safe mode because that's what my machine learning algorithm tells me. The reactor operator is going to sit there and scratch his head and go, why? Why did I just trip offline? I was just happy. I just got my coffee. What the hell's going on? So you're going to query your database. You'd like to query. In the old days, this was very laborious root cause analysis, right? You'd sit and you'd pull these logs and you'd look at the pressures and you'd go, well, we had a pressure spike right there. You say, well, that shouldn't have caused that. But in the new world, where are we now? We're stepping out into a new place where we can have a conversation with the generative component of an AI, which is sitting on top of that network of information data associated with your turbine control system, with your turbine generator set. All those transducers feeding into all that data, now you can query the data and say, what were the conditions just immediately before the trip? What do you think was the cause of the trip? So now the algorithms of the machine learning are going to be feeding information into the generative component, and the generative component, this is the cool part, is going to create language. So it's very sophisticated, fill in the blank kind of stuff. It's going to create a language response back to you, tokens being bashed back and forth. And the result is it's going to speak to you and say the conditions were this, and it'll give you an engineering list of the conditions that were going on beforehand. The artificial intelligence generative component is feeding your real intelligence information. And then you can ask another question, a probative question on that, and say, out of all other GE, Mark X, whatever, turbine systems, what were the root causes of reactor trips associated with the turbine trip? Then it'll search across all of the database that the vendor has, across all of their installed base, trying to answer your question through the generative component. All of a sudden, you have access to the root cause analysis reports being fed back to you through a generative generator from some other facility that actually did the root cause analysis on their trip that was similar to yours. Somewhere in the end of that is a human that is looking at the top 3 or 4 options and going, I'll bet you it was this. That human did a function called command broker. It's looking to try and create a command to restart or not, but it has to broker that command across the multiple inputs that it's receiving. Look at how high up in the stack you are with all of the information that is being synthesized and analyzed to get to the point where you have a selection of 4 or 5 opportunities to restart your plant. Based on what you now see in this list of 4 or 5, you, the real intelligence, can now ask the artificial intelligence to pull data associated with trying to figure out which of these 5 options is the specific one in your case. You have amplified human intuition because your intuition is leading you into the brokering of these different options. You've amplified human intuition through a combination of machine learning on the transducers and a generative AI sitting on top of that data that has access to a lot of other information. That's kind of where we are. We're at the edge of that, and we're still exploring the pieces that are very interesting and troubling are what happens next. These are all, I forget the terminology, but they're the early stage of AI. It's not the general AI. These are closed form AIs, if you will, or that's the term, narrow. These are all the applications I've been talking about are narrow AI, or a subset of that called machine learning. In that mix, if you put a generative form on top of where the machine learning is, then that reactor trip that it executed may or may not have happened the way you wanted it to, because that component of generative is very indeterministic. You don't know. And that emerged behavior, that question, that's enough of a question for, I believe, the regulators of the future to say, that's not going to be acceptable. You cannot use generative for that function.
Well, and that as well, takes us, I think, directly into the next stage of this conversation, because the reason I came up with this term, inevitability curves, back in the early 90s, because I was just seeing this is the future. In that case, everyone gets on the internet, and that was so hard for people to think about. I finally had to start saying, just assume for a minute it is. Let's look at the lines that connect now to then, over the next, say, 30 years from now, where we are now. And in fact, everyone's here.
Mm-hmm.
You have to think through these things. And when I look at the complexity of infrastructure, right, where we have been in my little lifetime, in our, post-industrial revolution, short period of time, and where we're going. Are we going to less complex systems that are less critical? No, quite the opposite. And what bounds, what I would see as an inevitability curve are not the possibilities, but the impossibilities. Are we going in 20, 50, 100, 200, 1,000, 10,000 years going to be going this direction or that direction? Are we going to be doing more handwork in this case, or are we going to do more automation? So for the purposes of argument anyways, we're going to do more automation, lots and lots and lots and lots more. And everything you said is also true, so that there's future versions of ourselves who will have figured these things out, or we can't have infrastructure. So, I think you've led up to a lot of these things, but whichever way you want to take it, what are we not going to do? What's completely off the table that people are expecting to be part of this in the medium to distant future in 30, 50 years, beyond perhaps you and I time, but enough that we should worry about it now.
I think that there's a paper I wrote a few years back on the transformative initiative that Asante and I kicked around for a while. I came up with this idea, and I said, we're going to get to a point where we're going to automate with complexity to the point where the systems themselves, or the system of systems, as the case may be, becomes very brittle to failure. And the failure is going to be extremely difficult to figure out. It's going to be trans-conceptual. You're not going to be able to conceive of the failure. So, and there are limits to what we can conceive of a failure. And sometimes we have the big button on the wall that says, give it to God, let the higher being sort this one out. So when you get into the position like that, the transformational initiative really takes into account kind of like the inevitability. The complexity is going to happen. It's going to keep getting more and more complex, and it's going to get to the point where human conceptual abilities fail. So you're not going to be able to actually see and understand, absent the genius level that can see things. You're not going to be able to see and control. So how do you get around that? Well, in the industrial control spaces, there is a connection between the logical weirdness of the world, this fantasy world, and in the virtual world, which mimics a power plant, for instance, which the computers are operating. So there's this thing that's out there, a virtual power plant, digital twin, if you will. There's this digital twin that the computers are operating. But there's a real twin too, and it's the thing on the ground. It's the thing that's flying through the air. It's the thing navigating through your arteries with a surgical probe at the end. It's these things. That real thing, it does have specific strength of materials and limitations of its design basis again, right? And what happens when you get beyond the design basis is the structural integrity will probably fail, or if it doesn't fail the structural integrity, then maybe you put an elbow joint into a position where it can't recover, so it breaks. One of the ways that we came up with, this was something I helped design in the early days. You remember the Aurora vulnerability, right? Everybody remembers the Aurora vulnerability, an asynchronous attack against a rotating AC machine. Well, if you look at the physics of what's going on with the Aurora attack, there is an industrial control system that has opening and closing breakers. But there's also this real machine out there that when you open the breakers, it starts to go faster. And when you close the breaker, it slows down dramatically right now, right? But when you open the breaker, it starts to go faster. Well, you can program the logic for preventing it from going faster into the control device that is actually being manipulated to open and close the breakers. But that's the one the adversary already owns. That's a hyper-complex system. It's a system of systems. It's on the end of your SCADA. It's a circuit breaker or something. Somebody far, far away is manipulating that breaker, not you. As a matter of fact, they probably denied you activity, and they're probably showing you what they want you to see. But if you have a device that's over on the box that's spinning, the turbine, the generator, if you have a box on it, outside of this digital realm, outside of that digital twin, if you have that box, which is only associated with that device, turbine generator in this case, and its only connection to the world is the close coil on that circuit breaker, then as soon as that circuit breaker gets opened and the design parameters are exceeded by this local box, it will send it'll send a signal over here, hardwired, that will prevent the close coil from energizing. Basically, it won't close. Therefore, the circuit will remain open. Therefore, other protections in the system will trip the turbine. You've just prevented an Aurora attack by thinking very local on the industrial control device that you're monitoring. That envelope is not associated with any of this other stuff. It's associated with the grid physics of that thing you're trying to protect. These envelopes, we have forgotten how to make them. We don't do those anymore. It's a very simple circuit. And when you look at the logic and you look at the physics of the DFDT curve, the acceleration curve based on frequency, you can plot a very simple plot of where you don't want that closed coil to be energized. And if you get a signal that tries to close it during that, if the signal doesn't go where it's supposed to go, it doesn't close. It's a transformational initiative to transform the way in which you approach the solution to a problem by not trying to put all the solution into one set of things, but by creating a thing, part of the machine, part of the turbine, part of the generator, that's built up through the supply chain of the generator that comes with it. And that is the component which prevents the destruction of the generator.
And I was hoping you'd go right there with that, because I think it wraps. I think we're sort of rapidly agreeing on this one, but I want to see about that, because one of my favorite things in all of industrial control systems, industrial systems in the modern era, were the bimetallic bearings of steam locomotives in the 1800s.
Oh, absolutely beautiful, weren't they?
Oh yeah, because if you're operating a train and you're going down the track, and those bearings overheat, you break your equipment, you're going to die and break a lot of other things. But your nose actually works really, really well, and you can smell it, because that bimetallic bearing will smell different as the temperature rises.
Mm-hmm.
And I think there's something of an analogy to that with where we're going with AI and all this stuff. Because as you just said, there's Aurora. For those who out there who don't know about that, Google up Aurora, Idaho National Labs. Basically, imagine a locomotive-size generator being hacked into and smoking and burning itself to death. And to your point, Tim, we can and we know how to engineer things that just don't fail. And I think, as we arc forward, we're not talking a couple of years, but maybe over the next couple of decades, we start, as you just said, putting that back in. Let's not build things that will just be, fail on the mechanical basis when we can do
Mm-hmm.
that. And with the time compression of AI, really enable operators to do the math, crunch numbers fast enough to stay on top of the complexity of modern infrastructure.
Yeah, pretty much it. So in a document I've written for some other people, asked me this question early on. Bright line criteria: where can generative apply and where can machine learning go? Machine learning is already being done. Very advanced software-enabled systems using machine learning algorithms right now, and they're doing very, very well, and it's very fast. Another term of art that's involved in this is the command broker function. There's a set of commands that are given on SCADA systems across critical infrastructure, focusing on critical infrastructure, not non-critical infrastructure, stuff that leads to extreme consequences, billions of dollars lost, hundreds of lives lost, etc. Critical infrastructure. There's a thing called a command broker, where the AI, if you will, feeds the commander, whoever the commander happens to be, a series of opportunities to enhance performance of the system and or save the system from destruction. And these options have to be selected by the command broker. You have to broker whatever that function is. Most of the software vendors I've been dealing with, which are pretty much the normal top 15, 20 across the globe, they understand these terms cold. Command broker is very important to them. Autonomous behavior of a machine learning component that's the electrohydraulic control system digital twin. I mean, that's autonomous control. It does it all by its lonesome. No one has to say, I think you should trip the reactor. It's gone before you can even think about, well, maybe I should trip the reactor. So it's already done its performance. There is no command broker. It's already done by the machine learning algorithm, which is very deterministic, or at least reasonably deterministic. The artificial intelligence version of that, with the generative component being far more indeterministic, it is generally felt by my supplier friends that a commander in the seat, a command broker function, needs to be there. That's part of the bright line criteria. So no autonomous behavior beyond a certain point in criticality. Therefore, with no autonomous behavior, you have to broker the command. Command broker is a trained operator. It's what we have today. But to your point, that command list, that you will, that you're going to have to broker across, that command list can be quite a lot. Those machine learning algorithms and that generative AI can give you a really beautiful list of all kinds of cool stuff. But as we've seen in far more trivial implementations of generative AI, some of those commands, opportunities that it may post on that list of things you can select, oh, do number 5. Some of those commands may be hallucinations. Some of them could be extreme biases. In an industrial control setting, you don't typically get to misogynistic behavior in your industrial control systems, but there is another kind of aberrant behavior that you can get. And some of those opportunities that you're supposed to select from may not be the best one. So your command and the experience with the machine, the industrial process, that's going to give the ability to get the best selection of that criteria, best selection off the list, or the selection that's not even on the list. That's the relationship between critical infrastructure, autonomous behavior, machine learning, and generative AI, which requires a command broker. That's kind of like the bright line criteria in a nutshell.
Well, it's always fascinating talking with you, and if I don't say it too often, it sincerely amazes me that I get to just have these conversations, right? And you and I have discussed it before, and I think that's a defining characteristics of sort of our community, is we're all sort of standing here going, is this real? Are we really talking about this? And we are, right? And someone has to figure it out, and I think it's in pretty good hands, right? I have a lot of trust with our community. You and I may be, approaching the end of our, active involvement in this stuff, but I see a generation coming up behind us that are native to a lot of these things, that have the vested interest, that will keep coming up with the solutions to keep all of this stuff working indefinitely.
Yeah, it's going to be fascinating. I hope to stick around for a bunch of it yet.
Yeah, that's right. I'll go for the Brokaw's brain option if necessary, just so I can observe the whole thing.
Yeah.
But let's end the recording here and have more conversations later. Everyone else, thanks for coming along the ride with us. Thank you very much, Tim, for the time today, your friendship, and everything else you've done for the world and the industry.
Yeah, thank you for being there, Chris.
My
Take
pleasure.
care.
Thanks, folks.